Hiya, welcome back. Glad to have you here with me to do some more calculus. Today we're learning partial fractions, and our learning objective today is to decompose fractions in order to integrate them. So far, we've been able to integrate fractions, such as this guy, by using the technique of u substitution. So we'd say u equals x squared minus 7x plus 10, and then du equals 2x minus 7 dx. And that's lovely, because there we have 2x minus 7 dx. But now we need a new approach to integrate rational expressions such as these. If we were to use u substitution on this first one, maybe you would try u equals x squared minus 1, and then du equals 2x dx. And this x here is not represented at the top. And then the second one, maybe u could be x squared minus 7x plus 10, and then du would equal 2x minus 7 dx, but that doesn't match what's up here. And then this last one, I don't know, u equals x plus 4 could be a way to start, but then du equals dx, and we've done nothing with the top. So that's not going to work there either. We know from algebra way back when that 2 over x plus 3 plus 4 over x minus 7, if you find a common denominator, you can rewrite that as 6x minus 2 over x squared minus 4x minus 21. We know how to integrate the left side, but we don't know how to integrate the right side. So basically, we need to figure out how to go from this complicated one to this easier to integrate one. In a proper rational expression, the degree of the numerator is less than the degree of the denominator. So let's consider a proper rational expression shown in the equation below. 2 over x squared minus 1 is equivalent to negative 1 over x plus 1 plus 1 over x minus 1. The expression on the right side of the equation is called the partial fraction decomposition. The fraction on the left has been decomposed into partial fractions. And that's what we're going to learn, is how to go from the left to the right. So again, we looked at this one at the beginning, but if you first see this problem, you think, well, maybe I could use u substitution. Du equals 2x dx, and we have a problem, right? That's not helpful for us. The next thing I would try would be to factor it, which is a good start no matter what, just to see, what's going on in this fraction. So if you factor it, you get 1 over x plus 2x minus 2. But from there, we don't have a technique. There's nothing to cancel to make it more simple. So this is where the decomposition comes in. We're going to rewrite this as two fractions with a on top of the x plus 2 and b on top of the x minus 2. Then we'll multiply both sides by a common denominator. And the common denominator is going to be the bottom of this left side here. So we'll multiply everything by x plus 2, x minus 2. Let me clear this up to make it look prettier. Okay, now on the left side, the top and the bottom are now the same, so that just becomes a 1. Over here, where the a is, the x plus 2's cancel out, and where the b is, the x minus 2's cancel out. So we can rewrite that whole thing as 1 equals a times x minus 2 plus b times x plus 2. Next step is going to be to find the zeros for a and b terms. If x equals 2 if x equals 2, that whole a term disappears. So we get 1 equals a times 2 minus 2, this guy's gone now, plus b times, now I plug in 2 for every x, so I end up with 4b equals 1, you see that? So b is 1/4. Now, if x equals -2, the b term disappears. So this guy's gone, and then I plug in -2 for x, and what does that give us? We've got 1 equals -4a, so a equals -1/4. Now, those will be able to plug in for a and b. Now we have something that we can integrate. So we can take each of these separately, and we get -1/4 ln of the absolute value of x plus 2 plus 1/4 ln absolute value of x minus 2 plus c. And ta-da, we're done. Let's try another one, a little bit more complicated, but the process is the same. Again, if you start with u substitution, it doesn't work. So then you have to kind of backtrack and think, well, what else could I try? Factor it first to see if you can cancel anything. You can't. So now we're going to work on our partial fraction decomposition. So we've got a over x minus 5 plus b over x minus 2. Now multiply both sides by the common denominator, which is going to be the bottom of the fraction on the left. This time the left looks a little bit different, doesn't it? Because this x minus 11 doesn't cancel out anywhere. So that one's just going to stay. And then the x minus 5 cancels on a, and the x minus 2 cancels on b. So now we have x minus 11 equals a times x minus 2 plus b times x minus 5. And then we'll find the zeros for those a and b terms. So if x equals 2, the a term disappears. So we'll plug into for the x on the b term also. So 2 minus 11, what's that, -9. And b times 2 minus 5, we get -3b. So b equals 3. And then looking at this b term, if x equals 5, the b term disappears. So we're going to plug in 5 for all of our x's. So 5 minus 11, that's -6. And then over here we get 3a. So a equals -2. And now we can plug those in for our a and b terms. Now we've got two things that we can integrate much easier. So we'll integrate each part. You get -2 ln quantity x minus 5 plus 3 ln quantity x minus 2 plus c. Next one, 3x plus 6 over x squared plus 3x. Again, you typically try u substitution first. So maybe u would be x squared plus 3x. But then du would be 2x plus 3, and that is not helpful. So the next thing we're going to try is we can factor. If you factor the bottom, nothing can cancel out. Actually, if you factor the top, you get 3x plus 2. That's not helpful. So, we'll just not do that. Now you'll notice as I'm working through these problems, I'm trying to walk you through sort of a thought process. Try u substitution, try factoring. If those don't work, maybe it's partial fraction decomposition. So we're going to split this into two fractions, a over x, b over x plus 3. Multiply both sides by the common denominator, x over x plus 3. You get 3x plus 6 equals a times the quantity x plus 3 plus bx. Looking at the a term, x equals -3 would zero that out. So we're going to put -3 in for all of the x's to get rid of a for a little bit. And we'd solve and get b equals 1. And then x equals 0 would zero out that b section. So we'll plug in 0 for all of the x's. B gets eliminated for a little bit, and we get a equals 2. And we'll plug those in for our a and b terms. Integrate each of these pieces separately, and you're done. There's an alternate method that you may like. So we're going to do the same problem again, but I'm going to show you a different way to do it, or maybe a shortcut of sorts. So here's how this one works. We're going to ignore a's denominator and put in a's undefined. So look at this a term, okay? What would make that fraction undefined? Well, x equals 0 would make that fraction undefined. So we're going to plug in 0 for all of the x's. However, we're going to ignore that x that created the fraction to be undefined. Now we get 3 times 0 plus 6, so we get 6 over 3, so b equals 2. And that 2 gets put in for a. We'll do the same thing for b. Ignore b's denominator and put in b's undefined. So x equals -3 would make that guy undefined. So we'll plug in -3 for all of the x's except the part that is b's denominator. So we get -9 plus 6 is -3 over -3 is 1, and that becomes b. And now we're back to where we were before. So you can do either method, whichever one works with your brain. Sometimes knowing this alternate method is helpful when you get something complicated like this guy. So again, try u substitution first, but it won't work. Then factor the bottom and you get x plus 2, x minus 2, and we'll split that into now 3 different fractions. And you could multiply each of those fractions by the common denominator. It'll work just the same. Or we could do our alternate method. So the a term is undefined at x equals 0. So we plug in 0 for all of the x's, just ignoring the denominator of a. And you get -3. That becomes the a term. And then the b term, x equals -2, would make that one undefined. So we put -2 in for all of the x's, just ignoring b's denominator. You get -1. And then finally the c term, x equals 2 would make that undefined. Put in 2 for all of the x's, but ignore c's denominator. And you get 5. Now I can plug -3 in for a, -1 in for b, 5 in for c. And integrate each of those separately, and you're done. At the beginning of the lesson today, we talked about what a proper rational expression is, and that's when the power of the bottom is bigger than the power of the top. But this is the opposite of that. The power of the top is bigger than the power of the bottom. So what we're going to do is try to actually do this division problem so that we have something that's proper to work with. So this simple guy on the bottom, x plus 4, that would set up quite nicely for a synthetic division. So plus 4 becomes -4 over here. And I know we've done this in a previous lesson, but it's always good to review. And then we'll take the 3 and bring it down. -4 times 3 is -12. 8 plus -12 is -4. -4 times -4 is 16. -10 plus 16 is 6. -4 times 6 is -24. And we have a remainder of 9. So now our problem looks like this. 3x squared minus 4x plus 6, and the remainder of -9 over x plus 4. Now you can integrate each of these pieces separately, and there we have it. X cubed minus 2x squared plus 6x minus 9 times the natural log of x plus 4 plus c. Now, if I were to first look at this problem, I would try factoring and canceling first. X squared plus 1, and I don't get anywhere. So that didn't work. That's okay. What else could I do? The top is bigger than the bottom, so I could use synthetic division. But remember, when you use synthetic division, that you have to plug in zeros for those coefficients that are missing. So really, we did x cubed plus 0x squared plus x plus 0. That's where those came from. And now we can zip through our synthetic division, bring down the 1, multiply, and add. 1 times 1 is 1. Add those, you get a 2, 2, and 2. So our new problem is x squared plus x plus 2 plus 2 over x minus 1. Integrate each of those pieces separately, and you're good. The hardest part of these problems is figuring out what technique to use. Do I use U substitution? Do I factor and cancel? Do I use integration by parts? But I keep trying to show you that just try different things. And if they don't work, then that's not the technique you use. Try a different one. This one's pretty tough to factor and cancel, but we still have the top bigger than the bottom. But since the bottom is so complicated, guess what we get to use? Long division of polynomials. So we've got 2x cubed plus x squared minus 11x plus 20 being divided by x squared plus 2x minus 3. All right, so we ask ourselves, look at this first term and this first term. What do I need to multiply by x squared to get 2x cubed? Well, I need to multiply that by 2x. And then this 2x, we multiply through that polynomial. Subtract. So we've got negative 3x squared minus 5x, and then we'll pull down the 20 and do it again. So what does x squared have to be multiplied to get negative 3x squared? Well, we have to multiply that by negative 3, and then we'll distribute this negative 3 through to x squared plus 2x minus 3. Whoops, there we go. There's the 20. And we'll subtract. This time we have a remainder of x plus 11. Now when we look at this one, we're like, okay, 2x minus 3, that's pretty, that's easy to integrate. But this guy, guess what we need? We need partial fractions to continue integrating the rest of the expression. So I'm going to go through the partial fractions pretty quickly because the main point of these problems is to show you just how you can combine techniques to solve a problem. That would decompose into negative 2 over x plus 3 over x minus 1. And then now we can integrate each of those pieces separately. This time we're going to combine U substitution with partial fractions, okay? So let's let U equal cosine x, du equals negative sine x dx. That's great, we're working so far. So what we get is negative 1 over U times U plus 1. Well, what do you do with this? Time for partial fractions again. So we're going to split it into A over U plus B over U plus 1. Using either method, you would get A equals negative 1 and B equals 1. And we'd plug those back in to our A and B spots and then integrate each piece separately. And in the end, we'll just have to plug in U back in. Last one, we'll do some U substitution and partial fractions again. So if I look at this, my initial thought would be to say, okay, let's let U equal e to the x, du equals e to the x dx, and I get 1 over U squared minus 1. which we can factor. This is a difference of squares into u plus 1, u minus 1. And then I'll go ahead and decompose it using either method. We get a equals negative 1/2, b equals 1/2, and then those we can plug back in. Take the antiderivative of each part separately and plug u back in. And I went through those last couple problems pretty quickly. Again, just showing you how you can use multiple techniques within one problem. It's like a 2-for-1 bonus. So thanks for hanging in there with me. These take practice, so grab some practice problems like your homework and have fun. Thanks for being here.